All right. I don't know why it stops. Maybe it only records a certain amount of memory. Okay, so suppose the bag, we just did this. If you have a bag that's 30 by 50, 30 inches by 50 inches, gives you 1,500 square inches, and if you multiply that by by 1 pound per square inch, you get 1,500 pounds. And the pressure provided by that vacuum is a little more than 1 pound per square inch. So if the bag hadn't gotten cut by the foot, it would have worked. Now explain why a suction cup sticks to a glass surface and why a book does not. Or in the case of my hand, the suction cup sticks to the board, but if I put my hand on there, it doesn't stick to the board. Why, Andrew?
Because the suction cup creates a vacuum which doesn't let the air that pushes out, so it's all just like all the pressure is pushing in.
So if I want to show the air pushing on the suction cup using arrows, this is glass, this is a suction cup, where do I draw the arrows?
Down.
Down. Kind of from always perpendicular to the surface. How about pushing up from underneath? No, that's what makes the suction cup work. When you push the suction cup against the glass, it's designed so that all the air squirts out the side and then can't get back in. It tries to push back in, but as it pushes back in, it just pushes the suction cup tighter. So there's no air under here. I'm just going to write no air pressure. And if you gave the example of a book or some other thing, this is a book. A book's going to have air pressure pushing here, air pressure pushing there, and it doesn't seem like there's air underneath it, but anything that's not sticking to a surface like a suction cup does have air under it. It doesn't have a seal. So that's why I can walk across the room and not go, because my feet get air pushing underneath them.
If you had suction cup shoes, would that work?
Yeah.
That'd be all sick.
Yeah, sort of. I don't think anybody would wear them much.
But you'd be able to like walk up walls and stuff.
Yeah.
Well,
no, not really.
Because they're huge. They can hold
Well, the problem
What
with
you'd have to do is you'd have to
walls-
have a thing that where like if you did it at a certain angle like those, you
Yeah.
can pull it off.
So this is good right now because there's good friction. It's being held against the wall and there's friction. But sometimes if you pull this way, the force is holding against the wall. There's nothing stopping you from sliding it. But unless you have good friction. So you need something like this where you can climb and then you can, with your hand, loosen it up with these little things. Did I tell you that's what they're for? So it's got these little thingamabobs here. Pinch them together, and that lets the air back in. So then you don't have the suction force anymore.
You could put a little string on the edge of it so you could like pick it up and then put it back down.
Right. Like you're kind of a self-controlled puppet.
Yeah.
Okay, so the jar can be, I don't think did I show you the jar thing
you have
last
to have pretty
class?
strong abs.
Did I?
To walkable.
No? This thing has had a hard life. It used to work great. I left it in the sink. I don't know if it's going to work now. Has anybody ever seen somebody do this before?
Flip it over and pull the thing out.
Actually, well, Megan, will you turn that camera so Lena will be able to see this? Thanks. So we'll see if it works. This is just a card. This was somebody's planner from last year. They gave it to me. They didn't use the planner. And if I do this, and let go, it stays there. It's actually working better now that it's soaked. So there's a simple explanation for why this works. And there's more complicated. The simple explanation is good enough for me. What's holding up the water? I bet you can guess. Just blurt it out.
Air.
Air pressure. And it's air pressure pushing up against this card. Pascal's principle, I always forget to put it in the notes. He discovered that air pressure in a fluid, or pressure in a fluid, was pretty much equally distributed and pushing in all directions perpendicular to surfaces. So pressure does push up and it pushes down.
Is
What?
that the same thing that happens when you like put your thumb over a straw?
Yeah, it is. Now, that's a simple answer. That's good enough. You could just write on that paper what I'm gonna write, which is air pressure is pushing up on the car and holding the water up.
But also, isn't that like the water sucking down would like be making like a vacuum and it doesn't have enough
Yes.
weight to...
So the nuanced answer is, well, wait a second. When I do this, there's air inside this jar, and it's connected to the room. It's the same pressure. So right now, this car isn't sticking. There's air in there, there's air out here, there's pressure in both places. When I turn this over, there's still air pressure inside, but what happens is that the second I let go of this, the water starts to fall. And as the water starts to fall, is it compressing or stretching out the air that's trapped in here? That air right there is the water. If water moves down,
It's
is
like
it squeezing it or stretching it?
Stretches.
Stretching it, and would that make it have more pressure or less?
Less.
Less. So what really happens is, as this water starts to fall, there's less pressure in there than there is outside, because that pressure decreases. So there's a pressure difference. There's stronger pressure pushing up, weaker pressure pushing down, and there's enough of a difference to hold up the water.
Would it work if you like, cause the card like keeps it from spilling out when you tip it, if you like, could you take the card away and then would the water like be able to
No.
stay there? That'd be so cool.
Yeah, that would be really, yeah, you've got to have something for, you've got to have a surface that doesn't flow like the water. Nick?
So if you, I saw you flip it over again and again, and it's still.
Yeah,
if you, like, shook
there's some
it
other
down-
things going on. There's, you'll learn about hydrophilic and hydrophobic things. Certain types of materials are attracted to water. Oil and water, they don't mix. If I had an oily card or a waxy card, I don't think this would work as well because it doesn't tend to stick to water. There's a little bit of sticking
But
going
if
on
you
there.
went like that and tried.
If I did it really fast,
Yeah, with the card fall, if you like tried to make it fall with the water. Yeah.
yeah.
How come it doesn't do that when you just turn it?
When I turn it, I'm not going to spend time figuring that out right now. I don't know. I don't have a quick answer for you. I might think about it later and I'll tell you later. But I want to move on. Never going to get to what I wanted to get to. Oh well, this has been okay, I guess. So explain why. The simple answer is air pressure pushes up on the card. If nothing else, this demonstrates that there is pressure pushing up. It goes in all directions. And now I kind of spoiled this one. People don't usually know the answer. I think somebody might in here. Anytime something floats, if you have a bubble floating, if you have a balloon floating, if you have a piece of wood floating, it could be a wood floating in water. It could be this rock floating in this water. If I push it down, somehow
Wait, that rock's floating.
this rock is floating. Yeah, I don't know whose rock this is. I think it's Mrs. Harrington's. That rock's sinking, this rock's floating. Somehow, what do you know is different about these two rocks?
Is it big?
The density. Somehow this one's got air trapped in it, a lot of empty space.
Can't you put those in a fire and they blow up? Like rocks? with air
Maybe,
in them?
yeah. If they're
Like a
really
rock?
trapped
I
bubbles.
found a rock like that big and I put it in fire and it just exploded.
In fact, last year, I'm never
Well,
gonna.
that's just from the heat.
Last year I blew up part of a concrete pad. Does anybody ever, if you go out of the building that way and you go out toward the fields, off on the right, there's some bocce courts. Have you ever heard about those? Megan, we turn that back over. It's all right. And near the bocce courts, there's this concrete pad, and Mr. LeGros, who's a chemistry teacher, does thermite reactions and things
Oh,
where he
thermite,
creates
so
fire and heat. And last year we were going to we used friction to make a fire in physics on the last day, and we had a little cookout. And we thought we would do it on this concrete pad. My students said, that's a good place. So we did it there. And right at the end, we just finished roasting marshmallows and hot dogs, and suddenly the concrete blew up into the air. All these chunks about this big went up 5, 10, 15 feet, out in every direction. And luckily, nobody was standing next to it. But what's that?
I thought we were on.
We had been there. The fire was there. It was going, but we were cleaning up, and for some reason nobody was there. It just exploded. Now there's this crater. And what we think is that over time there was a crack and water got down in that crack, and somehow the fire sitting over it built up pressure. It pretty much boiled the water, and when the pressure wasn't strong enough, it blew up the concrete. So that's why you're never supposed to use river rocks in a campfire,
That's what I
because
was
they can
saying,
have
yeah.
water trapped inside them. And when water goes from liquid to gas, it expands a lot and builds up pressure and explodes. Back to this though. Things that float, they don't have brains. How do they know which way is up? They always go up. This rock, it's less dense, yes, that's why it floats, but how does it know to go that way? Less dense things will always go up without a brain. How do they, Devin?
They're just following the path of less stress or something.
They're following the path to lower density, but how do they know? How do they follow it? They don't have a brain.
They're just like
Cameron.
there's less pressure higher, so like the top of the balloon knows that there's less
Yes.
pushing on it.
Yeah. So I'm going to draw the wrong picture first, and I'm going to fix it. So I'm going to draw pressure pushing from every side of this balloon. This is, Pascal says that the pressure in a fluid, in this case the fluid is the air around the balloon, pushes in every direction against surfaces perpendicularly. But what Cameron was just saying is these arrows should not all be the same length. Which arrow should be the longest?
The ones on the bottom.
The lower you go, the more air pressure there is. So I'm going to just work my way down, making arrows a little bit longer as I go. And then this will look right. So the net effect of this, if the pressure gets stronger and stronger and stronger, is that there's more force pushing up than there is down. If you filled this balloon with lead, would it float? No, if you filled it with lead, then even though there is buoyancy pushing it up, it's not strong enough to make it float. If you took the lead out and it doesn't weigh very much anymore, then it can float. So we all have buoyancy. Right now, there's buoyancy lifting us up. We're in this ocean of water, we're at the bottom. If all of a sudden the water disappeared, we would get a little bit heavier because it wouldn't be lifted the same way. But it wouldn't be, we wouldn't notice it. But all the helium balloons in the room, they'd fall. Well, and we would pass out and we'd get hickeys and our blood would boil and stuff like that. Oh, nosebleeds. You get nosebleeds too because your nose has capillaries really close to the surface. So if the pressure goes away, suddenly the pressure from inside your blood vessels in your nose, that bursts out. So I think we covered 15. 10:36. We get out of here at 10:53, right?
Yep.
Okay. So there's something else we got to do. This is slightly. This was very confusing last class. I'm going to try to do better than I did last class. What I was trying to do is skip over some stuff because there's no way we can get to everything I wanted to do. So I was trying to skip over unnecessary parts and come back to them later.